good evening. I hope you guys are doing all right. My name is Ian Coates, and welcome there to week 11 of Math 1031 here at Georgian College. We've got two PowerPoints there for your viewing pleasure there today, and we're introducing the whole topic of probability, and which is leading us up into next week there when we start getting into we take this to the next level. We start combining probability with that Gaussian curve that we introduced there last week. The whole idea there that within the first standard deviation, okay, there's 68%. Within two standard deviations, there's 95% chance, and then within three standard deviations, there's 99.7%. That's kind of where we're heading to, but we can't get there to where we want to go until we finish off this week here. So this is a fun one. Welcome to it. Let's get on with it, shall we? Before we begin, I need to make this perfectly clear that when you're dealing with percentage, because that's essentially what probability is, right? Like, what are the odds of winning? The probability of losing, right? All these kinds of things here. When you're talking probability, you're really talking percentage. And I just wanted to make it perfectly clear that where we're at here, you need to be able to flip in and out of percentage, decimal, and fraction at any given point in time. Okay? Percent goes from 0 to 100%. Decimals, relative to percent, they go from 0 to 1, where 0 is 0 probability, 1 is 100%, right? And then you've got the fraction as well. They all mean the same thing, okay? And you can even look at ratios as well, okay? Which I might add there next year. But you'll see there that these all mean the same thing. Half of a pizza is equal to 0.5 of a pizza, which is equal to 50% of a pizza. Being able to flip in and out of these guys here, you have to be able to do. So it's easier there to go from decimal to percent, because 0.3 would be 30%, right? And then this one here, 30% would be 30 out of 100. All right? Or it can just be 3 out of 10. Okay? 80%, 0.8, 8 out of 10, right? 8 divided by 10, which equals 4 divided by 5, right? Put that into lowest terms, right? And that one there is 0.8, right? 0. Okay, 3/5, okay, is equal to 0.6, which is equal to 60%. Have some fun with these. If you can fill these in, it's just on a testing situation, you might see a fraction, you might see a decimal, you might see a percent, but you have to realize there that when you're dealing with probability, the likelihood of an event happening, these all mean the same. And don't forget, lowest terms as well. All right? Let me know if you guys have any issues with that. All right. So welcome to the fundamentals of probability theory. A random experiment is a procedure which produces a set of possible outcomes whose occurrence depends entirely on factors outside the control of the person performing the experiment. Makes perfect sense, right? We want an experiment to happen like it would in nature. I don't want to be a part of it. I just want to observe it. It's what we call a random experiment. So Amelia is making a random experiment. She is rolling a fair-sided die, right? 1 die, 2 dice. The list of possible outcomes is 1, 2, 3, 4, 5, 6, right? Okay, so one die has 6 sides. There are your 6 sides, right? So an outcome is a specific and unique result of an experiment. You know, you let an experiment happen. What is the outcome? What is going to happen? Okay. Amelia is making the random experiment. She is rolling a fair-sided 6 die. and she rolled the die, and she got a 5. Whew. Heavy-duty science here. An event is a collection of outcomes that possess some trait or characteristic. We typically use capital letters A, B, C to denote different events. In the PowerPoint here, you will see P bracket A, so the probability of event A happening. Sometimes you will see P bracket E bracket, the probability of an event. You'll see both of these there. So you remember there that Amelia rolled the dice here. Okay. She got the outcome, so she rolled the dice 3 times here, right? 3 times. And she got the outcomes 1, 5, and 5. So together these outcomes may represent the event. All 3 rolls are odd numbers. Interesting stuff. Okay. A simple event is an event that has only one outcome. A compound event, though, is an event that involves more than one outcome, or that is a combination of 2 or more events. To clarify, Amelia is making a random experiment. She's rolling a fair 6-sided die. Only one outcome is possible. The number rolled, the event is simple. Then she rolls the dice 3 times. This is a combination of 3 simple events. The event is a compound one. Many different combinations, right? If there's only one combination, then it's what we call simple. Sample space. This is important here. Sample space is the collection of all possible outcomes of an experiment. We use capital S to denote the sample space, written as a list of outcomes in curly brackets separated by commas. And you'll see what this means here. Same example, okay? She's rolling the dice. And so you look at the possible outcomes. So sample space, we're referring to all of the possible outcomes that are possible. How many times can I say possible? That's enough. The sample space is, so you'll see here that there's 6 faces on the dice, 1, 2, 3, 4, 5, 6. So, Amelia is going to roll, there's a 100% chance that she's either going to roll a 1, 2, 3, 4, 5, or 6. That's the sample space. If she's rolling 2 dice, though, the sample space is a lot bigger. Okay, right? Because you have 36 combinations. 1, 1, 1. I know it looks like 11, 12, 13, 14, 15, 16, but it's not. What they're doing is they're going, the one dice rolls a 1, the other dice rolls a 1. So there's your snake eyes. One dice rolls a 1, the other one rolls a 2, 1, 3, 1, 4, 1, 5, 1, 6. So that's all the possible combinations there, with the first dice being a 1. Second dice being a 2, 2, 1, 2, 2, 2, 3, 2, 4. You'll see the pattern here. First dice 3, 1, 2, 3, 4, 5, 6. First dice 4, 1, 2, 3, 4, 5, 6. First dice 5, 1, 2, 3, 4, 5, 6. First dice 6. Okay, and you'll see there that there's 36 possible outcomes. So the sample space for this experiment with 2 die, okay, is 36. 36 possible combinations. If there's only 1 die, there's 6. So you see that there. 1 die, 6. The other die, 6. 6 times 6, 36. Interesting. Okay, let's keep on moving. Probability is the likelihood that an event occurs. Okay? It's just basically the percentage, the likelihood, how likely is an event to happen. Is there 90% chance? That's pretty good. Or is there a 10% chance? Not so good. Okay? Is there a 100% chance that an event will happen? Or is there a 0% chance that an event will happen? Anyway, same Excuse me, where's my coffee? Same experiment. Amelia is making a random experiment. She's rolling a die. The die is fair. All right. So there are 6 equally possible likely outcomes. Therefore, the probability of rolling each die is 1/6, right? So there's 6 possible combinations there that we saw, right? We saw them right here. And because it's a fair dice, they all have the same chance of coming face up. So, and this is where we get 1/6. Because 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6. That's 6 of them, adds up to 6/6, which is 1, which is 100%. That is our sample space there. It all covers. So the probability of hitting a 1 is 1/6, which is exactly the same probability as hitting a 5, 6, 4, or 3. Now, look at this situation here where the die is unfair. There is biased. Now, bias is one of those words we never ever want to see in science. The whole point of science is to determine the truth, to uncover the truth, right? And bias means that there's a problem with the machine, the detecting. Maybe there's a problem there. We didn't remove a particular variable, so it's compromising our data. Maybe they're if myself as the scientist, if my experiment goes through, I'm going to be a bazillionaire, right? Because one of these big Elon Musk is going to pay me billions of dollars for my idea, right? So this thing better work. And if it doesn't work, then I don't get my billions. So, your bias is something there that we never want in science. So, in this particular case here, the die is unfair. It shows 6 in half of the cases. So the probability of rolling a 6 is a half, right? 50%. So if rolling a 6 is 50%, that means rolling a 1, 2, 3, 4, 5 is also 50%. So all of the 5 outcomes are equally possible and share the remaining 50% that's left over within the probability of 100%. Therefore, the probability to roll any number except a 6 is a half divided by 5, right, times 5 over 1, invert and multiply, right, you have 1/10. So there's a 10% chance of hitting one of those guys, 1, 2, 3, 4, 5, as opposed to a 50% chance of hitting 6. Okay, moving on. So what does probability mean? Key terms here. So the probability is the number of desired outcomes divided by the number of possible outcomes total. So in this case here, this example here is using P bracket E. It doesn't matter. You see P bracket A. Here we're talking E of the event. A would also be the event as well. So, and you see here the number of desired outcomes. This is what you want to happen. Okay, I'm rolling a dice and I want a 3 and a 4, right? So the number of desired outcomes divided by the total sample space. What are all of the possible outcomes? So if you have a 2 out of 10 chance, that means there that you have a 20% chance, right? There's also, I want to note here, what's called the complementary probability. And you'll see there at P bar, P hat, whatever you want to call it there. This is the probability of an event not happening. Okay, so if you look at this case here, if I want to roll, a 5, right? So there's 1 5 on the dice. There are 6 possible outcomes. So 1 divided by 6, right? 1 divided by 6, okay, is and then times by 100, right? There's a 16.7% chance of hitting that 5, right? I want a 5. There's 1 of them. There's 6 outcomes. 1 divided by 6. So there's a 16.7% chance of hitting a 5. Okay. Now, the complementary is hitting everything other than a 5. Okay, so if 100% minus that 16% will give us the complementary, right? Because the complementary is not talking about hitting a 5. The complementary is talking about hitting a 1, a 2, a 3, a 4, and a 6, right? So if this one here was 1 out of 6, right, 16.7%, so then this one here must be the number of desired outcomes. So it's 1, 2, 3, 4, and 6. So that's 5 possible outcomes divided by 6 total sample space. 5 divided by 6, right? 5 divided by 6 equals times 100 is there's an 83% chance that you're not going to hit a 5. And what is very, very interesting to notice is that the probability of an event happening plus the probability of an event not happening always adds up to 100% or 1, right? Because this was what, 16.7? This one here was 83.3, and 83.3 plus 16.7 most definitely adds up to 100. Okay? So, probability of an event happening, probability of an event not happening. It's called the complementary. Okay. So, identifying sample space events and outcomes here. So, Amelia stores many socks in her drawer of 3 different colors. So, Amelia's got 3 different kinds of socks, green, pink, and white, and they're all kind of randomly in her drawer. And she chooses 2 socks at random. What is the sample space for this experiment? What are all of the possible outcomes? Identify all possible outcomes in the event in which she gets 2 white socks. Is this event simple or compound? Identify all possible outcomes of the event in which she gets a pair of different colors. Is this event simple or compound? So let's have a look here. So, same questions highlighted in yellow here. What is the sample space for this particular experiment? Well, you've got 3 different colors, right? Where are we here? Right? So, she could choose a green green, a green pink, a green white. She could choose a pink pink. She could choose a pink green, a pink white. She could choose a white white, or a white green, and a white pink. And if you'll see there, that's exactly what we've got. Green green, green pink, green white. Okay, and notice there, you'll see here that I'll come back to that in a second here. Here you've got pink green, pink pink, pink white. Here you've got white green, white pink, and white white. So you'll notice there that you have 2 that kind of look the same, right? Here you've got a green white, here you've got a white green. Even though in theory they both look, you have 1 green sock, 1 white sock, look at the order. So they are not necessarily the same. Okay, order works here. Identify all possible outcomes of the event in which she gets 2 white socks. And is this event simple or compound? So event A, 2 white socks. Okay, so the event is white white. Since there is only a single outcome, this is a simple event. Remember that? Only one outcome, simple. Identify all possible outcomes of the event in which she gets a pair of different colors. Is this event simple or compound? Right, so we're only looking for for different colors, so that means there the green green is gone, pink pink is gone, white white is gone, leaving 6 events there left. It's what we call a compound event. Okay, let me know if you guys have any issues on that. Moving on. So, if the probability of an event, that's what that means. You might see A, you might see E, it doesn't really matter. So if the probability of an event denotes the probability, if P of A denotes the probability of an event A occurring, then this event, we write it in terms of this. Now, the probability of that event happening has to fall between 0, the meaning there the event will never happen, and 1 or 100%, meaning there that the event is going to happen. So, and just if that makes you kind of queasy, all it just means there is that the probability of an event has to be greater than 0, but less than 1. Right? Remember there that 1 equals 100%. Okay? So the sum of the probabilities of all outcomes is always 1. Right? You remember the dice? Probability of hitting a 1, 2, 3, 4, 5, 6 is 1, 6 plus 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 1, 6 equals 6, 6, which is equal to 1, which is equal to 100%. An event with a probability exactly equal to 0 is impossible. Okay. An event there with a probability equal there to 0.5, it's a coin flip. It's what we call 50-50. Okay. 0.5 is equal to 50%. It's a half, right? An event with a probability exactly equal to 1, 100% will happen. It's certain. It's going to happen, right? Just a little bit of probability rules here, kind of the same thing. It just kind of goes over everything here. Just have a look at it. You know, it just kind of summarizes where we've been, talking about sample space and all these kinds of things here. Okay? Have a look at that there. Good. Approaches for determining probability. Well, okay, you've got theoretical probability, you've got empirical probability, you've got subjective probability, which is a no-no. You know, even the whole idea there of calculating the odds, like what does that really mean, right? So, depending upon the situation we are analyzing, the probability of an event is determined by using one of these three approaches, and that's what we're going to look at there in the next couple slides. When calculating probability, we usually express the result as either a fraction in its lowest terms or as a decimal rounded to 3 sig figs. Okay? And it's like what I was saying there on the test and previously, you want to kind of stay away from rounding, okay, until the end. And I would never fault you for keeping more decimal places than you should, okay? If a particular question is asking there, you know, the answer to be to 3 decimal places, well, then give me 3. But in your calculations, you know what I mean, keep 4 or 5, okay? So rounding probability here. So a student ID has a random capital letter at the beginning. What is a probability it coincides with the student's first letter, the student's name first letter? So since there are 26 equal possible letters, A, B, C, D, all the way to Z, and only one of them matches the probability, right? So 1 divided by 26, right? There's there's 26 letters in a bag, and you can't see them. You stick your hand in the bag and you pull out a letter. What's your probability of choosing a particular letter that you want? Well, it's 1 divided by 26, and if you do the math, right? 1 divided by 26, right? And 0.03846,153. You want to calculate the percentage, multiply by 100. So there is a 3.8485% chance of that happening. So you have about a 3.8% chance of picking the letter that you want. Okay? So you'll see here that they've kept it in decimal form, which is perfectly fine, but you have to realize there that that is 3.84%. Okay? Remember that slide? What is that slide? 14? Remember this one right here. We give you the decimal. You have to know that that's a percentage. Okay? 0.3 is 30. 0.5 is 50. Okay? 0.0384 is 3.85%. Good. Where am I? There we go. I don't know why those are all a little off there. So what we've got going on here, there's your theoretical approach to calculating probability, and that's the formula there that you've seen already. The probability of an event happening is equal to the number of favorable or desired outcomes divided by the total number of possible outcomes. Exactamundo. Same as, where was it, right here? Right? Same formula. Okay. Good. Perfect. So, as well, you could even have a ratio. Okay, the number of desired outcomes, that's the top, colon, the number of undesired outcomes. Okay, that would be what we call there the odds. We'll get into these ones there. So just showing you their ratios. So the theoretical approach requires every outcome in the sample space to be known and to have the same likelihood of occurring. So if I want to roll a 5 with a fair dice, okay, there's one 5, there's one face on the dice there that has a 5, there's 6 faces on the dice that have 1 to 6 numbers. So we've already calculated the probability of rolling a 5. If I roll the dice, am I going to get a 5? Probably not. But the theoretical probability of rolling a 5 is 1/6, right? What was that, 16.7%? Now, doesn't have anything to do with the empirical, with actually rolling. This is the theoretical. Okay, so Amelia rolls a fair 6-sided dice. Determine the probability of the following events. Okay, what is the probability of rolling a 6? 1/6, right? What is the probability of rolling an even number? So that means they're 2, 4, 6. So that's 3 numbers divided by a total of 6. So that one right there, that's a 50%. Right? This one here was what? 16.7%. Rolling at least a 3. So that means there, I'm not interested in a 1. I'm not interested in a 2. I'm interested there in rolling a 3, 4, 5, 6. So that's 4 numbers divided by 6. Okay? Which is equal to, get my calculator out, 4 divided by 6. Which is a 66, okay, 0.7% chance, okay. So that's theoretical probability, and that's where we're going to kind of hang out. But there's, these are your examples right here, okay. There's all the answers there that you would need, as we already did them right here, right? Okay, so let's have a look here at empirical. You remember if I want to roll a 5, well, theoretically, there's a 1 in 6 chance of rolling a 5. But empirical probability is the ratio of the number of occurrences of an event to the total number of trials of the event. So here we're talking about real life data, right? It's all based on past data or direct observations like frequency. Ooh. Like look at this one right here. If I want to, I'm flipping a coin, heads and tails, right? There's only, the sample space is 2. You can only roll a head or a tail. So there's a, if I want to roll a head, okay, 1 divided by 2, so there's a 50% chance of rolling a head. And remember the complement probability, there's a 50% chance of rolling a tail, right? So, but that's your theoretical. What I just did there was I just flipped a coin 10 times in a row. And I got 8 heads and 2 tails. Right? That doesn't seem right. Because my probability is 50-50. But you see, the empirical probability here, we're actually counting what happened. All right? And there's something there that I need to note at this time. It's called the law of large numbers. Right? If the theoretical probability, 50% chance of flipping a head, 50% chance of rolling a tail. but I just did it 10 times, and I didn't get that. I got 8 heads and 2 tails. Well, that's a fact of the universe. I did it. These are my results. You cannot flaw it. I didn't cheat. But you see there, that's the way stats goes. If you take a small sample size, the numbers might be distorted. But the bigger sample size you take, what if I flipped my coin 100 times? 1,000 times? 10,000 times? What if I flip that coin 1,000,000 times? And you see what happens here now is that the empirical probability starts to come into contact and become the theoretical probability, right? Because I rolled that coin, I flipped the coin. I keep saying roll a coin. You don't roll a coin. I flipped that coin and I got 8 heads and 2 tails, which isn't right. But if I flip that coin 1,000,000 times, the law of large numbers states that if an experiment is repeated a large number of times, the empirical probability will approach the theoretical probability. Okay? So, very important concept. So if I flip that coin 1,000 times, I will start to approach and get close to 50% head, 50% tail, if the coin is legit. Okay? So again, more examples here. Amelia rolled a 6-sided dice 25 times and got the roll shown in the table below. So she rolled the dice 25 times. She got a 1 3 times, a 2 5 times. She rolled a 3 4 times, a 4 2 times, a 5 4 times, and a 6 7 times. Okay. Based on this, what is the probability that the next she gets 6 on the next roll? Do you think the dice is fair or biased? So here, the event occurred 7 times out of 25. What are we talking about? Rolling a 6, right? Because that's what the question is asking for. Based on this, what is the probability that the next roll will be a 6? Right? Well, rolling a 6 occurred out of 25 times. You got a 7. So here, the empirical probability states that rolling a 6 is 28%. 7 divided by 25, right? 7 divided by 25 total, right? If you add all these up, you get 25. So my empirical probability for this particular case was that Amelia, she got a 6 28% of the time, which is not what it should be, right? Because when we're talking a dice, right, there's 6 faces on it. If it's a legit dice, you got 1 in 6 chance of rolling any of the numbers, 16.7%. Well, what's going on here, people? Amelia rolled a 6 28% of the time. And it's exactly kind of the same example as what I was talking about there with flipping a coin. If your sample size is small, your numbers are going to be distorted. But the law of large numbers states, as you approach infinity, right, the empirical probability starts to look like the theoretical. So for a fair dice, the probability of rolling a 6 is, as we already calculated, there's your 16%. The difference between theoretical and empirical probability exists, but to decide whether the dice is fair, we need to know more complex methods. Okay, we're going to get there. All right. There's your law of large numbers. States that as you increase the number of trials, your empirical probability will move closer to the theoretical. Probabilities range from 0, that the event never happens, to 1, okay, where the event is a sure thing. Again, same thing, 0 to 100%, 0 to 1 with decimal. Okay, just a little note here. The odds of an event occurring, we hear that there with all these gambling apps that are out there. Please be careful of those. They're just preying on people. Okay, but the odds of an event occurring is the ratio of the number of ways the event can occur, success, to the number of ways the event cannot occur. So in this case here are the odds of an event, okay, is equal to the number of desired divided by the number of undesired. Now you notice there it's a little different. It's not total, right? It's what you're looking for divided by what I ain't looking for. And in this case here, it can be a fraction, decimal, percentage, right? Or you can write it as a ratio. And generally that's how odds are. There's a 2 to 1, right? When you see that, when you hear the odds are 2 to 1, that means that there are 2 desired outcomes to 1 undesired. So it's actually very favorable for you. So there's 3, the sample space, it would be 3. 2 of those 3 you're looking for, 1 of them is not. But so the odds of rolling a 7 with 2 dice are 6 to 30, or 6/30ths, or 1 to 5. Okay, we'll show you guys these there, and we'll move on there from those. Finding the odds here, 11 poker chips are numbered consecutively, 1 through 10, with the extra labeled as an extra 6. So there are 2 poker chips there, okay, with a 6, and then there's only 1 of each of the rest. 1, 2, 3, 4, 5, 7, 8, 9, 10. There's only 1 of those guys, 2 6s. So a chip is drawn at random, right? You put all these chips in a bag, you can't see any, and you draw one. Find the probability of drawing a 6. Well, since there are 11 chips, right, total, probability is what you're looking for divided by everything else. 2 divided by 11, which is 0.18, which is 18%. And just to show you that, 2 divided by 11, okay, is 18.18.18.18, okay? A chip is drawn at random. Again, number 2, find the odds of drawing a 6 and find the odds of not drawing a 6, right? So find the odds of drawing a 6 and find the odds of not drawing. So there you're asking for the complement. So the odds of drawing a 6, okay, number of chances to draw 6, number of chances to draw other numbers there. So the odds of drawing a 6, there are 2. Now, you see here, when we're talking the probability, it was 2 divided by 11 because that was all the chips that were in there. Odds is not so, okay? Odds, the number of desired to the number of undesired. So in this case here, 2 to 9. So the odds of this event, this horse coming in, is 2 to 9. And you'll notice 2 plus 9 equals 11, okay? The odds of not drawing a 6. Well, in this case here, it's the number of undesired to the number of desired, and you'll see there 9 to 2. Okay, so the odds of that horse not coming in is 9 to 2. Okay, good. Yeah. We just talked about theoretical approach. We've talked about empirical approach. There's also, there's subjective probability. And subjective, there's the opposite of subjective, which is science, which is truth, which is objective, objective, okay, objective. Here we've got subjective, right? This is where your opinion is involved, and this is not scientific, okay? This is based on emotion. It can change throughout the day because we're human beings and we change our mind all the time, right? So subjective probability is an educated guess of the likelihood that an event will happen. Some examples here: a therapist predicts the likelihood of a patient's flu symptoms being gone in the next 3 days. Yep, we've all heard that. Doctor says, yeah, your symptoms should be gone there 100% in 3 days. Now, it's not exact. The symptoms might be gone tomorrow, right? The symptoms might be gone by Saturday. Okay, it's just a rough estimate, an educated guess, right? You think you have a 50% chance of getting the job you applied for in the hospital. right? We've all done that, right? When you go for a job interview and your spouse asks you, well, hey, how'd it go? Oh, I don't know, man. I think it went pretty good. 50-50, we've all done that. A coach estimates the probability that his team will win the Grey Cup, Canadian football, at 1 to 7. Okay, so yeah, it's just rough estimates. Okay, you really don't want to use subjective probability at all when you're dealing with scientific data. This is a personal thing, about, I shouldn't say unimportant things, because getting a job is important, but it's all based on you and your personal feeling. Okay, so hence the word subjective. Determining the sample space. Now, sometimes things can get a little hectic, but there are ways to go about this here. In order to calculate probability using theoretical approach, it is first necessary to fully determine the outcomes in a sample space. For complex cases, we may want to use outcome tables or tree diagrams to accurately determine the sample space. And I'm just going to zoom in here, okay? And we were dealing with dice, right? And 2 dice, right? And here's your 1-1, and 1-2, and we're rolling a 1-3. These guys here, the first dice is always 1, second dice is always 1, and you'll see there that there are 36 possible outcomes when you're dealing with 2 die. Okay, and this is what we call an outcomes table. Everything is here. This is the sample space. You can never roll a 7 and a 6. Okay, sorry. There's another one down here. Here we're talking about cards. Now, maybe cards are your thing, maybe they're not, but there are 4 suits to cards: spades, hearts, clubs, and diamonds. Then you've got all the different variables here. You've got ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. All right, and you'll see there that all the possibilities are there. Okay, so the likelihood there of a heart that is an ace, right? 52 cards, 1 divided by 52, right? As well, these are what we call tree diagrams. And the whole idea here, when you're talking a coin, right? Like the odds of flipping a coin, or the odds of getting a head or a tail, right? There's only 2. And if it's a fair coin, then it's 50%, 50%, right? There's only 2 choices. But what if I combine, what is the probability of flipping a head on a coin and then rolling a die and getting a 3? So in this case here, you see, I rolled a head, and the possibilities here, I've got a tail and a head. So that section is done. Now, if I roll a head on the coin and then roll a dice, it's possible there that I could get a 1, 2, 3, 4, 5, 6. So here I head and a 3. So in this case here, this is what I'm looking for. I flipped a head and rolled a 3. Okay. Conversely, though, what if I flipped a tail, and then you have 1, 2, 3, 4, 5, 6. These are tails, right? So this is what we call a tree diagram, and you're able to calculate probabilities and these kinds of things. It kind of makes things a little bit easier. Here's just another one here as well. Okay, if I can zoom up here, and just the whole idea here that there's 2 choices, 2 choices, 2 choices, and you'll see there that in order to get to this particular probability, that means there, okay, 1p, 2p, right? There's a 50% chance, a 50% chance of getting a p or an n. So here, p, 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 triple p, 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 n, p, p, n. Here, p, n, p. Okay, these are just talking about different events. So what this means here, PNP, what is the probability of this event happening? And what event is that? Well, that means they're getting a P and then an N, right, as opposed to a P, right, because there's two choices, and then another P again. So there's three events happening here, okay? There's getting a P, an N, and a P, and that's what that one means there. So anyway, just introducing these guys here because we're going to come back to these there at the next PowerPoint. Let's have a look here. Outcome tables organize the outcome of two compound events in a table, right? Remember our dice? Okay, you have one dice and another dice. Two different things going on here. Where the results of the first event are listed in the rows against the results of the second event. Okay, so here we're talking dice 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So here is 1, 1 rolling snake eyes. You can kind of see, and all the way down here having a 6 on both. So let's have a look. Amelia rolls two fair-sided dice. What is the probability that the sum she gets is at least 5? So that means there you got to add up all the different, there's 36 combinations there, and once you add them, you need a number of at least 5. Well, 6, 6 is 12, 6, 5 is 11, 10, okay, you go through, these are all greater than 5, and, you know, if you roll a 4 and a 1, that's at least a 5, a 3 and a 2, 5, 2 and a 3, 5, and a 1 and a 4, 5. And that means there that there are 1, 2, 3, 4, 5, 6 possibilities of not rolling, okay, two numbers there that add up to at least 5. All right, so what is the probability that the sum she gets is at least 5? Well, 6 of them, 6 out of 36 are not going to be at least 5. We see that. 1, 2, 3, 4, 5, 6. 6 out of 36 are not going to do it. So in this case here, right, we got to get rid of those 6, get them out of here, and we just want to calculate this probability right here, because all of these numbers are greater than 5 once you've added them together. So in this case here, 36 minus 6 divided by all total outcomes, right, which equals 30 divided by 36, which is equal to 5 divided by 36, which is equal to 0.833, right, 5 divided by 6, okay, times 100. So there's an 83% chance that Amelia is going to roll two dice that when they add up together, they will be greater or equal to 5. Okay? Now remember, that's theoretical. That ain't empirical. Empirical is the real data. So she rolls two dice, and guess what? She got a stinking 4. Right? 2 plus 2. You know, it's like she went against the odds, right? There's an 83% chance that she's going to hit all of these ones in here, right? But the empirical doesn't necessarily follow the theoretical probability. The empirical probability only emulates or begins to look like the theoretical once you use a large sample size. Okay? So in a tree diagram, each outcome is represented by a branch of the tree. We use tree diagrams when there are more than 2 pieces of information that need to be recorded. So this example here, I don't think we're asking any questions here at this point in time, but we're just kind of setting this all up here. Amelia and Brandon are planning to have 3 kids. Determine the sample space for possible outcomes of boys B and girls G. So the first child can be a boy or a girl, right? That's it, right? Heads, tails, okay? So if the first child is a boy, we're going to be on this side. If the first child is a girl, we're going to be over here. Now what about the second? Well, again, there's only 2 possibilities, right? Boy or girl. And what about the third? Okay, and you can see here what's happening. So the second boy can be second child can be a boy or a girl. The third child can also be a boy or a girl. So what we've got going on here, if the first child is a boy, second boy, third boy, that means BBB. Boy, boy, boy. Same with girl, girl, girl. right? But what if the first one there was a girl, second one was a boy, third one was a boy? That would be girl, boy, boy. You see how it's all working here? Okay, and order is everything. Okay, because you're gonna you're gonna have situations here that are look this similar. Here I have GBB. Here I have BBG. Two boys, one girl. Here I had the same thing. Two boys, one girl. But you look at who's going to be the oldest, right? The first one here born was a girl, right? Girl. So she's going to be the oldest. Eldest sibling, middle child, okay, youngest child. Not the case here. In this case here, the oldest child would be a boy, the middle child would be a boy, and you'd have a little baby girl. Okay, she would be the youngest. So, the whole idea here that order does matter. So in this case here, the sample space is 1, 2, 3, 4, 5, 6, 7, 8. Okay, 1, 2, 3, 4, 5, 6, 7, 8. There are 8 possibilities, right? And you look at this right here, right? If I have 2, what's 2 to the power 3? I have 2 choices, boy or a girl, and I do this 3 times. 2 to the power 3, 2 times 2 times 2 is also 8. Interesting. All right, last slide for this PowerPoint, and please know that there is another PowerPoint for this week 11 that you should watch. It takes all of this information on probability and expands it a little bit. So, determining the sample space using a tree diagram here, a student randomly chooses the answers for a quiz consisting of 3 true or false questions. So true or false questions, this is kind of nice, right? You have correct or incorrect. It's 50-50. It's kind of like flipping a coin. Or the previous example, having a boy or a girl. There's a 50% chance of having a boy, 50% chance of having a girl, and true or false is the same. So there's correct and incorrect. And we've got 3 true or false questions. So it's eerily similar to this one here. You have 1 event, 2 events, and the third child is the third event. Here we've got true or false questions, 3 of them. It's kind of the same thing. So, what is the probability that she will answer correctly for at least 2 questions? Okay, so let's do our tree. Okay, so first question, correct or incorrect? So you got the first question correct. Now again, the second could be correct or incorrect, and then correct or incorrect, right? So C, 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 correct, correct, correct. And you just label these here. Correct, correct, incorrect, which is what we have here. You have correct, incorrect, correct, CIC. Sorry, you can't see that there. There we go. You still can't see it. Okay. This one here, you've got correct, incorrect, incorrect. So this one here, you'd have 2 wrong and 1 right. So you see how these are here, and you just go around, you just go along, and the question is asking you, what is the probability that she will get at least 2 questions correct? Well, the question is asking you to go through all of your different outcomes here, possible outcomes, and pull out and calculate the probability that they have at least 2 correct answers. So this one here, I'm just going to zoom in a bit. This one, 3 incorrect answers, no good. This one here, 2 incorrect answers, no good. 2 incorrect answers, no good. Okay, so there's 1. Okay. ICC, right there. Here's 2 correct answers. CIC. All right, correct, incorrect, correct. We skipped over this one here. If you can see it there, correct, incorrect, incorrect. So that's 2 incorrect answers. We don't want that one. Okay. Sorry, my horrible animation. Again, correct, correct, incorrect. So that one has 2 correct answers. This one has 3 correct answers, which still falls into that same category. So there are 4 possible outcomes where she will get 2 answers correct. There are 8 in my sample space, So 4 divided by 8. So there's a 50% chance that this student will get at least 2 of those questions correct. Okay, 2 out of 3. All right. So that's what we've got going on there. That's the first PowerPoint there. We'll see y'all in a couple minutes there for the second one. Thank you.